James Webb found something that shouldn't exist. Hundreds of bright red objects in the early universe, objects that are too massive, too compact, and appeared too early. Scientists call them little red dots. 3 years later, they still don't know what they are. I'm going to walk you through why this is one of the biggest unsolved problems in cosmology right now. If that sounds interesting, subscribe, and let's get into it. The launch of the James Webb Space Telescope marked a definitive turning point in the history of our species, a moment when our technological grasp finally caught up to our questions about the cosmic dawn. For decades, astronomers had peered into the abyss with the Hubble Space Telescope, pushing its optical capabilities to the absolute limit. Yet the earliest epoch of the universe remained shrouded in an impenetrable fog. Hubble, for all its glory, was blind to the specific wavelengths of light that carry the secrets of the first billion years. As the universe expands, it stretches the light traveling through it, pulling the ultraviolet and visible glow of the first stars into the infrared spectrum. To see the beginning, we needed an eye capable of seeing heat, an observatory designed to capture photons that have been journeying through the void for over 13 billion years. Webb was built to be that eye. Its massive gold-coated mirror and cryogenically cooled instruments were engineered with a singular purpose: to pierce the veil of cosmic history and reveal the epoch of reionization, the time when the first lights turned on. When the telescope opened its shutter to the universe, the scientific community anticipated a specific view of our origins. Models predicted that the first galaxies would be faint, ragged collections of gas and primitive stars, slowly assembling themselves from the primordial soup. Astronomers expected to see the slow, clumsy waltz of gravity pulling matter together over eons. The deep field images that returned to Earth in late 2022 and throughout 2023 were supposed to confirm these theories, offering a higher resolution version of the story we had already written for ourselves. Instead, the data shattered those expectations almost immediately. Amidst the glittering arcs of gravitational lensing and the majestic spirals of mature galaxies, something else was lurking in the deep background. Scattered across the velvet darkness of the ancient universe were hundreds of intense crimson pinpoints. These were not the faint, diffuse blobs of gas that theory predicted. They were compact, bright, and overwhelmingly red. Initial scans from major surveys like Aegir and Fresco began to catalog these anomalies, revealing them to be abundant in the epoch between 600 million and 1.6 billion years after the Big Bang. The scientific community found itself staring at a phenomenon that had no place in the established timeline of cosmic evolution. These objects, casually dubbed little red dots, appeared in the data with a frequency that was statistically unnerving. They were not mere artifacts or noise. They were physical structures of immense power, existing at a time when the universe should have been in its infancy. The identification of these objects required a fundamental shift in how astronomers processed deep-field imagery. Unlike the sprawling galaxies of the modern universe, these entities were so compact that they appeared as unresolved points of light, indistinguishable from stars to the untrained eye. Yet their redshift placed them near the very edge of the observable universe. To understand why these objects have caused such a stir in the astronomical world, one must look at their physical impossibility. The little red dots are defined by a startling contradiction. They are incredibly small, yet impossibly bright. Detailed measurements reveal that these objects are extraordinarily compact, with an average radius of roughly 2% of the Milky Way. While our galaxy spans over 50,000 light-years from its core to its edge, a typical little red dot is confined to a radius of less than 500 light-years, with many squeezing into a space smaller than 150 light-years. Within this microscopic volume, they emit light with an intensity that suggests a stellar population comparable to massive galaxies. The implications of this density are difficult to visualize. In our own stellar neighborhood, the nearest star to the Sun, Proxima Centauri, is over 4 light-years away. If we were to inhabit a planet inside one of these little red dots, the night sky would not be black. It would be a blinding wall of light. A sphere of space that currently holds only the Sun and Proxima Centauri would, in one of these objects, contain more than 1 million stars. The sheer gravitational pressure and radiation density in such an environment defy our understanding of stable stellar dynamics. Their color provides the second vital clue to their nature. While they appear blue in ultraviolet wavelengths, they shift to an intense, deep red in the optical and infrared spectrums. This is not merely the result of cosmic expansion stretching their light. The redness indicates something intrinsic to the object itself, a specific emission signature or a heavy shroud of dust filtering the light. When analyzed with Webb's mid-infrared instrument, the spectral data reveals a flattened slope in the near-infrared, a signature that typically suggests the presence of mature, older stars. This presents a paradox. As these objects exist in a universe that is ostensibly young, the most telling fingerprint of the little red dots is found in their light spectrum, specifically a feature known as the V-shaped spectral energy distribution. When astronomers break down the light from these objects, they consistently find a sharp dip at a specific wavelength, known as the Balmer break. This feature is caused by hydrogen atoms transitioning between energy levels and creates a distinctive V-shape in the data graphs. This spectral signature has become the primary diagnostic tool for identifying these objects, separating them from standard quasars or star-forming galaxies. It suggests a complex internal structure, perhaps a dense cluster of stars surrounding a central engine, but the exact composition remains a subject of fierce debate. The existence of the little red dots forces a confrontation with the standard model of cosmology, particularly our understanding of how galaxies and black holes form. The current consensus, built over decades of observation and simulation, posits a hierarchical model of growth. Small clumps of dark matter trap gas, which cools and collapses to form stars, creating small dwarf galaxies. Over billions of years, these dwarfs merge to form the massive spirals and ellipticals we see today. Central supermassive black holes are thought to grow in tandem with their host galaxies, feeding on gas and stellar material at a regulated pace. The little red dots violate this timeline. They appear to be fully formed, massive, and incredibly dense less than 1 billion years after the Big Bang. If these objects are powered by supermassive black holes, as many astronomers suspect, those black holes are far too large for their age. In the modern universe, the mass of a central black hole is usually a tiny fraction of the galaxy's total mass. In the little red dots, the black hole appears to be overmassive, potentially outweighing the stellar population around it. This suggests that in the early universe, black holes may have formed first or grown at rates that physically shouldn't be possible, breaking the theoretical limit known as the Eddington limit, which dictates how fast a black hole can feed before its own radiation blows away the food source. Furthermore, the stellar density of these objects challenges our models of star formation efficiency. Standard theory suggests that converting gas into stars is an inefficient process, with feedback from supernovae and radiation pushing gas away and halting the birth of new stars. The little red dots, however, imply a system where gas was converted into stars with near-perfect efficiency, or where gas was funneled into a central core at a rate that bypassed the usual braking mechanisms. This hints at a mode of galaxy formation that is fundamentally different from what we see in the local universe, a fast-track evolution that allowed compact, massive structures to assemble almost instantaneously on cosmic timescales. This connects to the broader mystery of dark matter. The formation of such compact objects suggests that the dark matter halos in the early universe might have had different properties, specifically low spin. If the dark matter halo spinning around a nascent galaxy has low angular momentum, gas can collapse directly into the center without being flung out into a disk. This would create exactly the kind of dense, spherical nuggets of light we observe as little red dots. It implies that the conditions of the early universe allowed for a diversity of structural formation that has since ceased, leaving these crimson anomalies as fossils of a forgotten epoch. Faced with objects that break the rules, theoreticians have been forced to propose exotic explanations. One of the most captivating hypotheses is that the little red dots are not galaxies in the traditional sense, but rather the observational evidence of population 3 stars. These are the hypothetical first stars of the universe, formed from pristine hydrogen and helium without any heavy metals. Theory suggests these stars could be monstrously large, hundreds or even thousands of times the mass of the Sun. Some models, such as those proposed by Nandel and Lobe, go even further, suggesting that under the right conditions, supermassive stars with millions of solar masses could form. These titans would be bright enough to be seen across the universe, and would possess a cool red outer envelope, matching the description of the little red dots perfectly. If this hypothesis holds, it would mean we are looking at individual stars of impossible scale, celestial monsters teetering on the brink of collapse. Such an object would eventually die by collapsing directly into a black hole, bypassing the supernova stage entirely. This leads to a related theory, the heavy seed scenario. If these objects are indeed supermassive stars transitioning into black holes, they would solve the mystery of how the earliest supermassive black holes grew so quickly. They didn't start small and grow. They were born huge. Another prevailing theory interprets the little red dots as a unique phase of inside-out growth. In this scenario, we are witnessing the birth of a galaxy's core before the rest of the galaxy has formed. The intense red emission comes from a compact starburst, or a feeding black hole shrouded in dust, representing the dense nucleus of a future elliptical galaxy. Over billions of years, these objects would accrete more gas to their outskirts, growing larger and bluer, effectively hiding their crimson origins inside a shell of younger stars. This would explain why we don't see little red dots in the nearby universe. They haven't disappeared. They have simply evolved into the centers of the galaxies we see today. There are even more exotic possibilities being discussed in the corridors of astrophysics departments. Some researchers speculate that the extreme density of these objects might allow for interactions between dark matter and normal matter that we cannot observe elsewhere. Others suggest they could be gray holes or quasi-stars, objects where a black hole exists inside a massive star, powering it from within like a parasitic engine. While these ideas border on the speculative, the extreme nature of the little red dots demands that we keep our minds open to physics that operates only at the limits of density and gravity. The quest to identify the true nature of these objects has mobilized a massive international effort, spearheaded by the Rubies program. Led by astronomers Anna de Graaf and Gabriel Brammer, this initiative is using the James Webb Space Telescope to conduct a forensic analysis of the little red dots. The primary weapon in this investigation is the NER SPEC instrument, a spectrograph capable of breaking the light from these distant faint sources into their constituent wavelengths. By targeting hundreds of these red sources in the ultra-deep survey and the extended Groth strip, the team is building a statistical library of their properties. This is not passive observation. It is an active hunt. The workflow involves identifying candidates in deep field images and then committing precious telescope time to stare at them for hours, collecting enough photons to build a reliable spectrum. The data is then subjected to rigorous modeling, comparing the observed light against templates of known stars, galaxies, and quasars. This process is complicated by the fact that the little red dots are often surrounded by other foreground galaxies, requiring sophisticated software to disentangle the light of the target from the noise of the universe. New technologies are being developed specifically to crack this case. The next generation of X-ray observatories, such as the proposed AXIS satellite, is being designed with the sensitivity required to peer through the dust of the early universe. If the little red dots are powered by black holes, they should be emitting X-rays. Current telescopes are often too blind to see them, but a new high-sensitivity X-ray eye could confirm the presence of an active galactic nucleus instantly. Simultaneously, ground-based, extremely large telescopes with 30-meter mirrors are under construction. These behemoths will work in concert with space telescopes, using adaptive optics to resolve the internal structure of these dots, potentially allowing us to see if they are point sources or tiny resolved galaxies. Collaboration is the engine driving this research. Data from Webb is often released to the public immediately, allowing teams around the world to compete and cooperate in real time. Papers are published on preprint servers within days of data downloads, creating a chaotic but rapidly advancing dialogue. Theoretical astrophysicists work hand in hand with observational astronomers, tweaking their models of the early universe to fit the incoming stream of impossible data. It is a golden age of high-stakes astronomy, where a single observation can rule out a decade of theory. The discovery of the little red dots is reshaping our cosmological narrative in real time. We are moving away from a model of slow, steady, hierarchical growth toward a picture of a violent, efficient, and rapid early universe. These objects tell us that the cosmos woke up quickly. The machinery of star formation and black hole construction was operating at peak efficiency almost immediately after the Big Bang. This implies that the conditions of the primordial universe were far more dynamic than our simulations predicted, rich with dense gas flows and extreme gravitational environments. If the little red dots are indeed the seeds of modern galaxies, they force us to rewrite the biography of the Milky Way. It suggests that our own galaxy may have started as a dense crimson nugget of light, growing its spiral arms only later in life. It challenges the relationship between galaxies and their central black holes, suggesting that the monster in the middle may have come first, acting as an anchor around which the galaxy subsequently grew. This reversal of cause and effect has profound implications for how we understand the architecture of the universe on the largest scales. Beyond the physics, the little red dots offer a philosophical lesson on the limits of human knowledge. We built the most advanced machine in history to look for something specific, and instead we found something completely different. It serves as a humbling reminder that the universe is under no obligation to conform to our models. The crisis in cosmology is not a failure of science, but a triumph of observation. It proves that there are still frontiers where our understanding breaks down, where the map ends and the territory begins. As we continue to study these crimson jewels, we are likely to find that they are the key to connecting the physics of the very small quantum mechanics and particle physics with the physics of the very large gravity and general relativity. They represent laboratories of the extreme, places where matter is pushed to its absolute limit. Whether they turn out to be supermassive stars, primordial black holes, or something entirely new, the little red dots have already succeeded in doing what great scientific discoveries always do. They have expanded the horizon of the possible, proving that even after billions of years, the universe still has secrets left to tell. To understand why these objects are breaking our cosmological models, we must look past the pretty pictures and examine the raw data that James Webb beams back to Earth, specifically the spectral energy distribution. When astronomers plot the brightness of these little red dots against their wavelength, they often see a distinct V-shape or checkmark pattern that defies standard classification. On the short wavelength end, corresponding to the ultraviolet, the light is often surprisingly blue and intense. In the language of astronomy, a blue slope indicates unattenuated, high-energy radiation, typically the signature of extremely hot, young stars, or the exposed accretion disk of a black hole. This blue continuum suggests that whatever is powering the object is not entirely hidden behind a veil of dust. Yet, as we move to the longer wavelengths, the optical light that has been redshifted into the infrared, the spectrum rises steeply into the red. This creates a contradictory picture where the object appears to be both unobscured and heavily shrouded at the same time. This duality forces researchers to construct complex geometric models, perhaps imagining a scenario where we are looking down the clear, open funnel of a thick, dusty torus, seeing the hot engine in the center while the surrounding structure glows with reprocessed infrared heat. The mystery deepens when the light is broken down further through spectroscopy to reveal the chemical fingerprints and kinematic behavior of the gas within these dots. The most striking feature found in many of these spectra is the presence of broad emission lines, particularly the line known as H-alpha. In the physics of glowing gas, the width of an emission line is a direct proxy for speed. Narrow lines come from gas that is drifting relatively calmly, perhaps floating in the interstellar medium of a galaxy. Broad lines, however, are the signature of violence. They indicate that the gas emitting the light is swirling at tremendous velocities, often thousands of kilometers per second. This phenomenon, known as Doppler broadening, occurs because some of the gas is rushing toward us and some is rushing away, smearing the specific wavelength of light across a wider range. When astronomers see these broad lines in the local universe, it is almost universally a sign of a Type I active galactic nucleus, or a quasar, where gas is whipping around a supermassive black hole deep within the gravitational well. If we apply the standard quasar equations to these little red dots, interpreting the broad H-alpha lines as evidence of a central black hole, the numbers that emerge are staggering. The velocity of the gas allows us to calculate the mass of the central object required to keep that gas in orbit. When this calculation is performed for the little red dots, it suggests black holes with masses millions or even tens of millions of times that of the Sun. In isolation, a 10 million solar mass black hole is not unusual. The one at the center of the Milky Way is 4 million solar masses. The problem arises when we compare this black hole mass to the mass of the galaxy that hosts it. In the local universe, there is a tightly correlated relationship known as the Magorian relation, which states that a central black hole usually possesses about 0.1% of the mass of the galaxy's stellar bulge. It is a tiny seed in a massive fruit. In the little red dots, this ratio is shattered. If the broad lines are indeed caused by black holes, then these black holes are not tiny seeds. They are monstrous pits, that constitute 10%, 20%, or in some extreme interpretations, nearly the entire mass of the object. We are looking at overmassive black holes, titans that have somehow grown to their maximum size before the galaxy around them had a chance to form. This reverses the traditional coevolution narrative where galaxies and their black holes grow in tandem. Instead, it paints a picture of a universe where the black hole comes first. A dominant gravitational sinkhole that formed rapidly in the early dawn of time, perhaps waiting for a galaxy to slowly coalesce around it. This black hole first scenario challenges our understanding of seeding mechanisms, forcing us to ask how a black hole could consume enough matter to reach 10 million solar masses in just a few 100 million years without blowing away its food supply. The mechanism of feeding a black hole is governed by the Eddington limit, a theoretical cap on how fast matter can fall in. As gas falls toward a black hole, it heats up and emits radiation. If too much gas falls in at once, the outward pressure of the light pushes the gas away, choking off the fuel supply. To grow these little red dots to such immense sizes so quickly, they would need to be feeding at, or potentially significantly above, this Eddington limit continuously for millions of years. This requires a supply of gas that is smooth, uninterrupted, and incredibly dense. While super-Eddington accretion is physically possible and observed in some transient events, sustaining it for the duration required to build these objects implies a cosmic environment far more dense and gas-rich than our simulations typically predict. It suggests that the early universe was not just a place of gentle collapse, but a realm of torrential inflows where matter cascaded into gravitational wells at catastrophic rates. However, there is a dissenting voice in the scientific community that suggests we might be misinterpreting the evidence entirely. The assumption that broad emission lines equate to a black hole is based on our experience with the local universe. But the early universe may have played by different rules. There is a possibility that these lines are not caused by the rotation of gas around a singularity, but by the explosive outflows of extremely massive stars. In the nearby universe, we observe Wolf-Rayet stars, massive, dying stars that eject their outer layers in powerful stellar winds. These winds can accelerate gas to high velocities, creating broad emission lines similar to those seen in quasars, though typically less extreme. If the little red dots are not quasars, they could be compact star clusters packed with thousands of these Wolf-Rayet stars, or perhaps a stellar population completely unlike anything we see today. This leads to the hypothesis of the top-heavy initial mass function. In our local galactic neighborhood, when a cloud of gas collapses to form stars, it produces a specific distribution. A few massive blue giants, a moderate number of sun-like stars, and a vast swarm of tiny red dwarfs. This distribution is called the initial mass function, IMF. But conditions in the early universe were different. The gas was hotter and lacked the heavy elements that help cool clouds down to form small stars. It is conceivable that in these first galaxies, the star formation process was biased heavily toward the top end. We might be looking at galaxies that formed almost exclusively massive stars, monsters hundreds of times the mass of the Sun. Such a cluster would be incredibly bright, blue in the ultraviolet, and the combined winds of these giants could mimic the spectral signature of a black hole. If this is the case, the little red dots are not black holes at all, but the most intense starbursts in the history of the cosmos, burning through their fuel in a frenzied flash of light. The implications of the stellar hypothesis are just as disruptive as the black hole hypothesis. If these objects are powered by stars, the sheer amount of light they emit implies a density of stellar material that borders on physical impossibility. We would be talking about packing the mass of 1 billion suns into a sphere only a few light years across. At these densities, stars would be so close together that they might physically collide, merging into even larger, unstable objects. This brings us to the theoretical domain of supermassive stars, single stars with masses of 10,000 or even 100,000 suns. Such objects have never been observed, and standard stellar physics suggests they should blow themselves apart almost instantly. Yet, some theorists propose that in the dense, distinct environment of the early universe, perhaps aided by the annihilation of dark matter particles within their cores, such leviathans could exist. These dark stars would be cool, red, and incredibly luminous, potentially matching the strange photometry of the little red dots. Whether they are overmassive black holes or hyperdense stellar clusters, the little red dots present a severe problem for the lambda CDM model of cosmology regarding the budget of baryons. Baryons are the normal matter, protons and neutrons that make up stars and gas. Dark matter provides the gravitational scaffolding, forming halos into which baryons fall. We have a good estimate of how many baryons should be available in a dark matter halo of a given size. The little red dots are so bright and imply such high masses that they seemingly require converting nearly 100% of the available baryons in their halo into stars or black holes. In the local universe, this conversion efficiency is very low, typically around 10% or 20%. Because feedback processes like supernovae and AGN jets blow the gas away and stop the formation process. For the little red dots to exist as interpreted, the early universe must have been nearly 100% efficient at turning gas into luminous matter. This lack of waste, this perfect efficiency, is unnatural in a chaotic system. It implies that the feedback loops we rely on to regulate galaxy growth were either absent or fundamentally different in the first billion years. The dust itself poses another riddle. The red in little red dot comes largely from the way dust attenuates light. But dust is made of heavy elements, carbon, silicon, iron, that must be forged in the hearts of stars and expelled through supernovae. The universe began with only hydrogen and helium. To have enough dust to shroud these objects so heavily at such high red shifts means that previous generations of stars must have already lived, died, and polluted the cosmos at a breakneck pace. It requires an extremely rapid enrichment cycle. We are seeing objects that look old in terms of their chemical abundance, rich in dust and metals, at a time when the universe was effectively a toddler. This forces astronomers to compress the timeline of the first stellar generations, leaving almost no breathing room between the Big Bang and the emergence of chemically complex galaxies. Furthermore, the compact nature of these objects, often unresolved point sources, even to the sharp eye of James Webb, means they are physically tiny, with radii often smaller than 50 parsecs. For comparison, the Milky Way is 30,000 parsecs across. Imagine compressing the luminosity of a significant galaxy into a space smaller than the nebula around a single star cluster. The radiation pressure alone in such a region would be immense. If these are star clusters, the photon density would be high enough to strip electrons off atoms and keep the gas in a permanent state of high ionization. This connects to the mystery of the epoch of radionization, the period when the universe transitioned from opaque to transparent. If little red dots are common, their intense radiation could have been a primary driver of this cosmic phase change. However, the dust complicates this picture. If they are shrouded in dust, the ionizing photons might be trapped inside, unable to escape and clear the intergalactic fog. This leaves us wondering if the little red dots were the heroes of reionization or merely selfish hoarders of light, burning brightly but keeping their energy confined within their own dusty shells. The confusion is compounded when we try to place these objects on the evolutionary tree of galaxies. Are they the ancestors of the massive elliptical galaxies we see today? If they are overmassive black holes, they might represent the seeds that eventually grew into the giants like M87. If they are dense star clusters, they might be the cause of future galaxies, waiting to accrete more gas and grow a disk. Or perhaps they are an evolutionary dead end, a class of object that thrived only in the unique high-density, high-pressure conditions of the early cosmos and then vanished, merging or dissipating into forms we no longer recognize. The green Pea galaxies found in the local universe, small, compact, and intensely forming stars, are often cited as potential analogues, but even they pale in comparison to the extreme densities and luminosities of the high redshift little red dots. The LRDs are green peas on steroids, operating at the limits of physics. Another layer of complexity is added when we consider the geometry of the observation. We are viewing a three-dimensional universe projected onto a two-dimensional sky. It is possible that some of the extreme properties we derive are illusions caused by orientation. If an accretion disk is viewed face-on, it appears brighter than if viewed edge-on. If the dust is arranged in a patchy distribution rather than a smooth shell, we might be seeing light leaking through holes in the curtain, leading us to miscalculate the total amount of obscuration and thus the intrinsic brightness. Simulating these clumpy, complex geometries requires immense computing power, and even then, the results are ambiguous without higher resolution data than even Webb can currently provide. We are trying to reconstruct the architecture of a house by looking through a keyhole from a mile away. The tension with the standard model of cosmology is perhaps the most exhilarating aspect of the little red dot problem. The lambda CDM model predicts a hierarchical growth of structure. Small things form first and merge to become big things. The presence of massive, fully formed, metal-rich, and potentially super black hole-dominated objects so early suggests that structure formation can proceed much faster than the steady march predicted by dark matter simulations. It hints at the existence of fast tracks in cosmic evolution, mechanisms that allow matter to collapse and organize at breakaway speeds. This might require tweaking the properties of dark matter itself. If dark matter is warm rather than cold, or if it interacts with itself, it could alter the way halos collapse in the early universe, potentially facilitating the rapid formation of the dense cores we observe as little red dots. We must also consider the role of cosmic variance. Webb's field of view is relatively small. It is drilling deep pencil beams into the sky. It is statistically possible, though increasingly unlikely as more surveys are completed, that we have simply stumbled upon a rare overdense region of the universe, a cosmic metropolis that is not representative of the average. However, the LRDs are popping up in multiple different survey fields, from Goods South to the Sears field, suggesting they are a ubiquitous population rather than a local anomaly. They are everywhere, lurking in the high redshift data, red sentinels that refuse to be ignored. Their ubiquity implies that whatever process creates them is a fundamental mode of the early universe, not a freak accident. The distinction between the stellar and AGN active galactic nucleus explanations is not necessarily binary. The universe rarely deals in absolutes. It is possible that the little red dots represent a hybrid stage, a transitional phase where the line between a star cluster and a black hole blurs. In the dense core of a collapsing protogalaxy, runaway stellar collisions could lead to the formation of a massive central object that is essentially a heavy seed black hole in the process of being born, surrounded by a nuclear star cluster that is also feeding it. We might be witnessing the very moment of birth for the supermassive black holes that anchor galaxies today, the missing link between the first stars and the first quasars. If so, the broad lines and the blue continuum are telling the story of a chaotic, violent symbiosis where stars and black holes are growing together in a dense gravitational mosh pit. The spectral analysis also reveals strange abundance ratios. In some LRDs, the strength of nitrogen emission lines is unusually high compared to oxygen. In the local universe, high nitrogen abundance is often a sign of gas that has been processed through the CNO cycle in massive stars and then ejected. This nitrogen loud signature supports the idea of rapid stellar processing or specific types of stellar winds. However, explaining the sheer quantity of nitrogen required to produce these signals again pushes the limits of standard stellar yield models. It forces astrophysicists to propose supersolar metallicity in these primordial objects, meaning they have more heavy elements than the Sun, despite existing when the universe was 98% hydrogen and helium. This paradox of evolved chemistry in an unevolved universe is one of the strongest arguments that our timeline of heavy element production needs a radical revision. As we stare at these photometric points of light, we are also contending with the limitations of our templates. Most of the software used to analyze galaxy spectra is calibrated on objects in the local universe or at moderate redshifts. We teach computers what a galaxy looks like based on what we see nearby. The little red dots are essentially out-of-distribution data. When a fitting code tries to tell us the mass or age of an LRD, it is forcing a square peg into a round hole, trying to match a primordial monster to a template of a modern spiral or elliptical. This systematic uncertainty means that the crisis might partially be a crisis of calibration. We may need to build entirely new libraries of synthetic spectra that account for the extreme physics of the early universe, higher temperatures, harder radiation fields, and different dust compositions, before we can truly trust the numbers we are deriving. One particularly intriguing possibility is that the dust in these galaxies is not the standard mix of silicates and carbonaceous grains we see in the Milky Way. If the dust grains are smaller, or composed of different materials like pure graphite or diamonds produced in the shockwaves of early supernovae, their ability to block and scatter light would follow a different set of physical laws. This would change our calculations of how much light is being hidden, potentially bringing the mass estimates down to more manageable levels. A gray extinction curve, where dust blocks all wavelengths more equally rather than preferentially blocking blue light, could radically alter the interpretation of the V-shape SED. Understanding the mineralogy of the first dust grains is therefore not just a matter of chemistry, but a key to solving the cosmological puzzle of the little red dots. The energy output of these objects is also raising questions about the thermal history of the intergalactic medium. If LRDs are as numerous and as energetic as they appear, they would have heated the gas between galaxies significantly. This heating affects how smaller galaxies form, as hot gas is harder to capture gravitationally than cold gas. A population of LRDs could essentially sterilize their surrounding environment, suppressing the formation of dwarf galaxies around them. This might explain why we see a deficit of small galaxies in certain environments, or alter our understanding of how the cosmic web was assembled. The little red dots are not just isolated curiosities. They are influential actors that shaped the thermal and dynamical history of their cosmic neighborhoods. There is also the faint end of the LRD population to consider. Currently, we are seeing the tip of the iceberg, the brightest, most massive members of this class, because those are the ones Webb can detect. But if nature follows its usual patterns, for every monster LRD we see, there should be thousands of smaller, fainter versions. These dim red dots might be the true building blocks of the early universe, hiding just below the detection threshold. Future deep field campaigns, staring at the same patch of sky for hundreds of hours, may reveal this hidden population. If they exist, they would contribute significantly to the total mass and light budget of the early cosmos. If they don't exist, and the LRD phenomenon is restricted only to the most massive objects, it tells us that this mode of formation requires a specific high mass threshold to trigger, a go big or go home rule of early galaxy formation. The narrative of the little red dots is currently being written in real time. Every few months, a new paper is published that either reinforces the monster black hole theory or creates a new avenue for the stellar burst theory. We are in the Wild West phase of discovery, where the data is sparse enough to allow for wild theories, but solid enough to rule out the boring ones. The certainty is that the standard model, in its vanilla form, is insufficient. It requires modification. Whether that modification is a tweak to the laws of star formation, a new understanding of black hole seeds, or a fundamental shift in the timeline of cosmic enrichment, the little red dots are the catalyst. They are the observational anomaly that precedes a paradigm shift. In the coming years, the extremely large telescope ELT and other ground-based giants will join the hunt. While they cannot match Webb's infrared sensitivity from the ground due to the atmosphere, their massive mirrors will allow for higher resolution spectroscopy of the brighter targets, potentially resolving the broad lines with greater precision and detecting fainter diagnostic lines that Webb misses. These future observations will help break the degeneracy between the different models. For instance, detecting high-energy X-rays would be a smoking gun for the black hole theory, as stars, no matter how massive, generally do not emit strong X-rays. Conversely, a lack of X-rays would heavily favor the stellar hypothesis or imply that the black hole is so buried in gas that even X-rays cannot escape, a Compton-thick scenario that implies even higher densities. Ultimately, the little red dots serve as a reminder that the universe at redshift 7 is not just a younger version of the universe at redshift 0. It is a different place entirely, with different densities, different chemistry, and different rules of engagement between gravity and radiation. We have stepped off the map. The familiar correlations that guide us in the local universe, the relations between mass and light, between bulge and black hole, between metallicity and age, are dissolving. In their place, we are finding a raw, unpolished cosmos where objects grow explosively, unconstrained by the feedback loops that will later tame them. The little red dots are the fossils of this chaotic epoch, glowing embers that tell the story of the universe's fiery youth. They are a problem. James Webb cannot solve alone, but they are a problem that has reignited the imagination of the entire field of cosmology, forcing us to dream of physics that is grander, stranger, and more dynamic than we ever dared to write into our simulations. To understand why this specific class of object creates such a profound headache for the established order, we must look closely at the spectral fingerprint that defines a little red dot. When astronomers disperse the light from these objects into a spectrum, they do not see the smooth, continuous curve of a typical galaxy, nor do they see the straightforward, jagged peaks of a standard quasar. Instead, they often see a distinctive V-shape that defies easy categorization. On the left side of the graph, in the ultraviolet and blue wavelengths, there is a faint, relatively flat continuum that looks like the light from young, hot stars. Then, the graph dips, only to rise dramatically in the red and infrared wavelengths, screaming upward with an intensity that implies something incredibly hot and compact is dominating the energy output. This unique V-shape suggests a hybrid beast, a galaxy that is seemingly unobscured in the ultraviolet, yet heavily reddened in the optical, a contradiction that implies a geometry we have never seen before. It is as if we are looking at a blazing furnace through a thick curtain of smoke, but somehow A pinhole of pure blue light is piercing directly through the center, unbothered by the dust that shrouds the rest of the system. This spectral duality is the first clue that the little red dots are not playing by the rules of the local universe, but the true crisis emerges when we measure the speed of the gas within them. By analyzing the width of the hydrogen emission lines, specifically the H-alpha line, which has been shifted by the expansion of the universe from visible red light deep into the infrared where James Webb operates, astronomers can measure how fast the gas is swirling. In a quiet galaxy, gas moves effectively at a leisurely pace, perhaps a few hundred kilometers per second. In the little red dots, however, the H-alpha lines are immensely broad, indicating that gas is whipping around the center at speeds exceeding 2,000, sometimes 4,000 kilometers per second. In the standard lexicon of astrophysics, such velocities have only one translation: gravity. Specifically, the intense gravity of a supermassive black hole. To hold on to gas moving that fast, you need a central mass of 10 million to 100 million suns, all packed into a volume no larger than our solar system. Here is where the mathematics of the early universe begins to break down. If we accept the testimony of the broad emission lines that these are indeed supermassive black holes, we are immediately confronted with a timeline problem of impossible proportions. We are seeing these objects at redshifts of 6, 7, and 8, which corresponds to a time when the universe was less than 800 million years old. To have a black hole of 100 million solar masses existing that early is like finding a giant sequoia tree in a garden that was planted yesterday. Black holes grow by eating gas, a process known as accretion, but there is a physical speed limit to how fast they can eat, defined by the Eddington limit. If a black hole tries to eat too fast, the radiation pressure from the infalling gas becomes so intense that it blows the food away, choking off the chaotic feast. Even if a black hole ate at this maximum theoretical limit continuously, 24 hours a day, for the entire history of the universe up to that point, it is mathematically difficult to start from a stellar remnant, the corpse of a single star, and reach the masses we are inferring from the little red dots. This forces cosmologists to reconsider the very seeds of black holes. For decades, the consensus was that supermassive black holes grew from light seeds, the remnants of the first generation of stars, known as population 3 stars. These seeds would be perhaps 10 to 100 times the mass of the Sun. But the existence of little red dots suggests that the universe may have employed a shortcut, creating heavy seeds through the direct collapse of massive primordial gas clouds. In this scenario, a cloud of gas does not fragment into stars, but collapses under its own weight directly into a black hole of 10,000 or 100,000 solar masses. This provides a head start, a way to jump the queue of cosmic evolution. Yet, even with heavy seeds, the numbers for the little red dots are tight. The sheer abundance of these objects, James Webb is finding them by the hundreds, suggests that if direct collapse is the answer, it was not a rare anomaly, but a common mode of formation in the infant cosmos. A realization that would require a complete rewrite of our theories regarding primordial gas thermodynamics and the role of dark matter halos in the first billion years. The plot thickens when we look for the corroborating evidence that should accompany such massive black holes. In the local universe, when we see broad emission lines and hot dust, we almost invariably see X-rays. As gas spirals into a black hole, it heats up to millions of degrees, emitting a piercing scream of high-energy X-ray radiation. To confirm the nature of the little red dots, astronomers have turned to the deepest X-ray images available, taken by the Chandra X-ray Observatory. They stack the X-ray data from the precise locations of the little red dots, hoping to see the telltale glow of accretion. The result was a deafening silence. The X-rays are missing. This is the Kossevsky paradox, named after the researchers who highlighted the discrepancy. If these are supermassive black holes consuming gas at the rates implied by their infrared brightness, they should be blazing in the X-ray sky. Their absence implies one of two disturbing possibilities. Either these black holes are buried behind columns of gas and dust so thick that even X-rays cannot escape. A Compton-thick cocoon that effectively hides the engine from view, or the objects are not black holes at all. If they are not black holes, the alternative is perhaps even more exotic. Some astronomers propose that the little red dots are actually extreme starburst galaxies, but not the kind we see today. They would have to be galaxies dominated entirely by massive hot stars, Wolf-Rayet stars, that blow powerful winds. These stellar winds could theoretically mimic the high-speed gas motions we see in the spectral lines, creating the illusion of a black hole where none exists. However, for this to work, the initial mass function, the recipe that dictates how many big stars are born for every small star, would have to be radically top-heavy. In our local neighborhood, for every massive star, the universe creates thousands of strange little dwarfs. To explain the little red dots without black holes, the early universe would have to be a place where dwarfs were forbidden, a cosmos of giants, where star formation produced only monsters. This would alter our understanding of chemical enrichment, as these giants would rapidly explode, flooding the young universe with oxygen, carbon, and iron far faster than standard models predict. The debate between the supermassive black hole hypothesis and the top-heavy stellar hypothesis is currently at a stalemate because James Webb has hit its own physical limit. The telescope sees the infrared light perfectly, but it cannot see the X-rays needed to confirm the black hole, nor does it have the spectral resolution to perfectly distinguish the complex wind signatures of a billion Wolf-Rayet stars from the swirling disk of a quasar. We are left with the little red dots as ambiguous anomalies, glowing red stop signs at the edge of the observable universe that halt our confidence in the standard model. They are compact, possessing radii of only a few hundred light-years, yet they shine with the luminosity of 1 trillion suns. If they are star clusters, they are denser than any cluster physics should allow, approaching the point where the stars would essentially collide and merge. If they are black holes, they are more numerous than the dark matter halos that are supposed to host them, violating the baryon budget of the cosmos. This baryon budget crisis is perhaps the most subtle yet devastating aspect of the little red dots problem. According to the lambda CDM model, the standard model of Big Bang cosmology, there is a fixed ratio of normal matter baryons to dark matter. Dark matter forms the invisible scaffolding, the halos, and normal gas falls in to create galaxies. We know roughly how massive these dark matter halos can be at redshift 7. When we estimate the mass of the stars and black holes in the little red dots, we find that in some cases, the visible mass accounts for nearly 100% of the available baryons in the halo. This is physically implausible. In the local universe, the process of turning gas into stars or feeding a black hole is terribly inefficient. Usually, only 10% to 20% of the gas is converted, while the rest is blown away by feedback. For the little red dots to be real, the early universe must have been a machine of perfect efficiency, converting every scrap of available matter into light and heat with zero waste. This suggests that the feedback loops, the supernovae and jets that regulate growth in the modern universe, simply did not work back then, or they worked in a completely different way that trapped matter rather than expelling it. Furthermore, the existence of the little red dots challenges our understanding of dust production. The red in their name comes from dust attenuation, which absorbs blue light and re-emits it as thermal infrared radiation. But dust is made of heavy elements. silicon, carbon, iron, that are only produced in the cores of stars and released via supernova explosions. At redshift 7 or 8, the universe is so young that there has been very little time for generations of stars to live, die, and pollute the cosmos with this dust. The little red dots are incredibly dusty, implying that the very first generations of stars were not only efficient at forming, but efficient at dying and spreading their ashes. We are seeing a universe that matured chemically at a breakneck speed, achieving a level of pollution in 500 million years that we previously thought took billions of years to accumulate. This rapid enrichment suggests that the pristine early universe, the era of pure hydrogen and helium, was a fleeting moment, almost instantly replaced by a cosmos choking on its own exhaust. The implications extend to the reionization of the universe. We believe that ultraviolet light from the first galaxies ionized the neutral hydrogen fog that filled the cosmos during the Dark Ages. If a significant fraction of the early galaxy population consists of these little red dots, their contribution to reionization is questionable. If they are shrouded in thick dust, the ultraviolet light cannot escape to ionize the intergalactic medium. It is trapped and converted to heat. This means the little red dots are photon thieves, stealing the ionizing radiation that the universe needs to wake up. If they are as numerous as JWST suggests, we may have a deficit of ionizing photons, forcing us to look for other sources, perhaps fainter, dust-free dwarf galaxies, to do the heavy lifting of clearing the cosmic fog. The little red dots sit there, hoarding their energy, glowing brightly in the infrared but potentially contributing nothing to the grand phase transition of the cosmos. As researchers scramble to fit these objects into simulations, they are finding that the standard code does not run. Put a little red dot into a simulation of galaxy formation, and it disrupts the evolution of everything around it. Its gravity is too deep, its radiation too intense. It suggests that our simulations are missing a crucial piece of physics. Perhaps a new mode of accretion, a new interaction between radiation and dust, or a modification to the properties of dark matter itself on small scales. Some theorists have even toyed with the idea of fuzzy dark matter or interacting dark energy to explain how such dense structures could form so quickly. The little red dots are not just an observational curiosity, they are a stress test for the entire framework of cosmology. They are the point where the rubber meets the road, and currently the road is tearing the tires apart. The resolution to this problem will likely not come from a single breakthrough, but from a slow, grinding accumulation of multi-wavelength data. JWST has done its part by revealing the population, but it is an infrared telescope, and the answers lie in the X-rays and the radio waves. Future missions, like the European Space Agency's Euclid, or the upcoming Nancy Grace Roman Space Telescope, will provide wider surveys to see just how rare or common these objects truly are across the entire sky. But the smoking gun will likely be found by next-generation X-ray observatories that can pierce the heavy obscuration. Until then, we are left with the spectral V, that dip and rise that signifies a mystery. We are looking at objects that are effectively baby quasars, but they are babies the size of giants, born into a universe that shouldn't have the resources to feed them. There is also the possibility that the little red dots represent a transitional phase that every massive galaxy goes through, a brief, violent adolescence that is obscured by dust and therefore invisible in previous surveys. Before JWST, we were blind to this phase because the optical telescopes like Hubble could not see through the dust, and the older infrared telescopes didn't have the resolution to separate the dots from the background noise. We may have been missing 50% of the story of galaxy evolution simply because it was hidden behind a red curtain. If this is true, The little red dots are the missing link between the primeval gas clouds and the majestic spirals and ellipticals we see today. They are the crucibles where the cores of galaxies are forged, compressed by gravity and shrouded in secrecy. The confusion is compounded by the variability of these sources. Some little red dots appear to flicker on timescales of months, a behavior that strongly supports the black hole hypothesis, as star clusters cannot change their brightness that quickly. However, not all of them flicker. This inconsistency splits the population into potential subcategories: the true little red dots, which are dusty AGN, and the imposters, which might be compact starbursts. Disentangling these two populations requires monitoring them over years, a campaign that is only just beginning. We are watching the universe in real time, waiting for a wink or a nod from these distant objects to betray their true nature. Every photon we collect has traveled for 13 billion years to tell us a story we don't yet know how to translate. What remains clear is that the high redshift universe is far more active, dense, and dusty than anyone dared to predict. The little red dots are the most extreme manifestation of this activity. They challenge the linear narrative of cosmic history, the idea of a slow, steady buildup of structure. Instead, they paint a picture of a boom-town universe, where structures grew explosively, ignoring the regulations of feedback and the limits of accretion. They force us to imagine a time when the laws of astrophysics were pushed to their breaking point, where gravity crushed matter into existence with a ferocity that the modern universe no longer permits. This brings us to the edge of what is knowable with our current tools. We can model, we can hypothesize, and we can simulate, but the little red dots sit there in the data, stubborn and bright. They are a reminder that for all our precision cosmology, for all our measurements of the cosmic microwave background and the expansion rate, we still do not fully understand how the lights turned on in the darkness. We have found the switches, these compact, red, heavy objects, but we don't know how they were wired. The problem James Webb cannot solve is not a failure of the telescope, but a triumph of the universe's ability to surprise us. It has handed us a puzzle piece that doesn't fit the board, and in doing so, it has told us that the board is bigger than we thought. The mystery of the little red dots also invites a re-examination of the local truth versus the distant truth. In astronomy, we often assume that the processes governing the Milky Way today are the same processes that govern the universe at redshift 7. We assume that black holes accrete the same way, that stars form from clouds the same way, and that dust behaves the same way. The little red dots suggest this uniformitarianism might be a fallacy. Perhaps the physics of the early universe was fundamentally different, not in the laws of nature, but in the environmental conditions. A universe that is denser, hotter, and more gas-rich might allow for modes of accretion that are impossible today. We might be looking at super Eddington accretion, not as a rare violation, but as the standard operating procedure of the early cosmos. If gravity can funnel gas faster than light can push it away, then the growth of black holes is not limited by time, but only by the supply of fuel. And in the early universe, the fuel was everywhere. This perspective shifts the little red dots from being anomalies to being the inevitable result of a gas-dominated cosmos. They are what happens when you have too much matter and too much gravity in too small a space. They are the runaways. If this interpretation holds, it solves the impossible mass problem by removing the speed limit. A black hole could grow from a light seed to a supermassive monster in a mere 100 million years, if the Eddington limit is merely a suggestion rather than a law. This would mean that the monsters in the centers of our galaxies today, Scrad, Assatrisk, and M87, are the dormant remnants of these frenzied feeding events. We are living in the quiet aftermath of the little red dot era. Yet, Accepting super Eddington accretion as a universal solution feels like a get-out-of-jail-free card for theorists. It requires complex hydrodynamics that are difficult to simulate. It involves magnetic fields, turbulence, and radiation transport in regimes we cannot test in a lab. We are effectively invoking magic physics to save our models. This is why the tension remains high, until we can observe the geometry of the gas flow, something that requires resolution far beyond JWST. We are guessing. We are detectives trying to reconstruct a crime scene from a blurry photograph taken 13 billion years ago. The little red dots are the bodies, but the weapon and the motive remain obscured. The scientific community is currently fracturing into camps. There are the AGN believers, who point to the broad lines and the high ionization as definitive proof of black holes. There are the stellar purists, who argue that we are underestimating the power of massive stars in low metallicity environments. And there are the new physics advocates, who see the little red dots as the first crack in the dam of dark matter theory. This intellectual conflict is healthy. It drives the design of new observations and new simulations. It forces us to scrutinize our assumptions about everything from atomic physics to galactic dynamics. The little red dots have revitalized the field of high redshift astronomy, turning what was expected to be a confirming survey into a radical questioning of foundations. As we stare at these red pixels, we must also consider the bias of our own observations. We see the little red dots because they are bright and because they are red. But what are we missing? Are there little blue dots that are obscured by even more dust? Are there big red blobs that are too faint to be picked up as point sources? The little red dots might just be the tip of the iceberg, the most extreme members of a population that fills the early universe. If they are just the outliers, then the average galaxy at redshift 7 might be stranger than we imagine. We are characterizing an entire epoch based on its loudest, brightest residents. It is like trying to understand human civilization by only looking at rock stars. The quiet, normal galaxies of the early universe, the ones that will eventually become the Milky Way, are still largely hidden in the noise, overshadowed by the glare of the little red dots. Ultimately, the little red dots problem serves as a humbling check on our cosmological arrogance. We thought we had the timeline of the universe mapped out: Big Bang, Dark Ages, first stars, regionization, galaxy formation. We thought we knew the actors and the script. The little red dots have walked onto the stage and started improvising lines that act as a jarring counterpoint to our carefully written narrative. They tell us that the universe was wilder, faster, and more efficient than we believed. They tell us that the connection between the visible light we see and the invisible mass we infer is not a straight line. And they tell us that even with the most advanced machine humanity has ever built, the universe can still keep a secret. We continue to watch, we continue to measure, and we continue to wonder what other monsters are hiding in the deep red shift, waiting for the next generation of telescopes to reveal them. The story of the early universe is not finished. In fact, thanks to the little red dots, we now know we are barely past the opening sentence.